Hi, I'm Shyamala Gauri, Assistant Professor in Rohini College of Engineering and Technology. CS 3301 Data Structures, Unit 4 Multi-Way Search Trees and Graphs. I'm going to explain the concepts about graph in data structures. A graph is an abstract data type ADT that consists of a set of objects that are connected to each other via links. These objects are called vertices and the links are called edges. Usually a graph is represented as G is equal to V, E, where G is the graph space, V is the set of vertices and E is the set of edges. If E is empty, the graph is known as a forest. Below diagram shows the graph. Example for graph structure. The terms used in graph are vertex. Each node of the graph is represented as a vertex. In the above example, the labeled circle represent vertices. Thus, A to G are vertices. Here, A can be identified by index 0, B can be identified using index 1 and so on. Edge represents a path between two vertices or a line between two vertices. In the example, the lines from A to B, B to C and so on represents edges. Adjacency, the two nodes or vertices are adjacent if they are connected to each other through an edge. In the example, B is adjacent to A, C is adjacent to B and so on. Path. Path represents a sequence of edges between two vertices. In the above example, ABCD represents a path from A to D. Next is a representation of graph. The graph is represented in two ways. They are adjacency matrix representation, adjacency list representation. First one, adjacency matrix representation. It is a V by V matrix where the values are filled with either 0 or 1. If the link exists between Vi and Vj, it is recorded 1, otherwise it is recorded 0. Here is the example. Here on the picture on the left side shows you the graph structure and the picture on the right side matrix shows you the adjacency matrix representation of a given graph. Nodes are written column wise and row wise A to E, and then there is no path from A to A, so the value is 0. There is a path from A to B, so value is 1, and there is a path from A to C, value is 1. There is no path from A to D, so value is 0. There is a path from A to E, so the value is 1. Likewise, for all the nodes, the values has to be filled. Then it forms the adjacency matrix representation of a graph. Next, adjacency list representation. It is a list of the vertices directly connected to other vertices in the graph. The left side picture is a given graph and the right side shows you when A is connected to B, so it is linked. B to C and then C to E. So it is shown as a linked list structure. Likewise, for all the elements, we can draw the linked list. Next is types of graph. There are two basic types of graph. One is directed graph, another one is undirected graph. Directed graph consists of edges that possess a direction that goes either away from a vertex or towards the vertex. The left side picture shows you the example of directed graph. Second is undirected graph. It have edges that are not directed at all. The left side picture shows the example for undirected graph. Next topic is breadth first search. BFS algorithm traverses a graph in a breadthward motion and uses a queue to remember to get the next vertex to start a search when a dead end occurs in any iteration. BFS employs the following rules. Rule 1. Visit the adjacent unvisited vertex. Mark it as visited. Display it. Insert it in a queue. Rule 2. If no adjacent vertex is found, remove the first vertex from the queue. Rule 3. Repeat Rule 1 and Rule 2 until the queue is empty. Here is an example for BSF. In the first step, this is in the traversal column, there is a graph, and in the description, I have shown the description what has to be uh, done to attain BFS algorithm. Here, first step, initialize the queue, and in the second step, we start from visiting S and mark it as visited. And in third step, we then see an unvisited adjacent node from S. In this example, we have 3 nodes, but alphabetically we choose A, mark it as visited and enqueue it. In the next step, the unvisited adjacent node from S is B. We mark it as visited and enqueue it. And in the next step, the unvisited adjacent node from S is C. We mark it as visited and enqueue it. Now S is left with no unvisited adjacent nodes. So we dequeue and find A. From A, we have D as unvisited adjacent node. We mark it as visited and enqueue it. At this stage, we are left with no unmarked nodes. But as per the algorithm, we keep on dequeuing in order to get all the unvisited nodes. When the queue gets emptied, the program is over. Next shortest route algorithm is depth first search. Depth first search algorithm traverses a graph in a depthward motion and uses a stack to remember to get the next vertex to start a search when a dead end occurs in any iteration. As in the example given below, DFS algorithm traverses from S to A and then A to D and then D to G, from G to E and E to B. There is no node from from B. So again it moves backward to E and to G, and then it goes to unvisited node F, G to F and then F to C. The above example employs the following rules for DFS. Rule 1. Visit the adjacent unvisited vertex. Mark it as visited. Display it. Push it in a stack. Rule 2. If no adjacent vertex is found, pop up a vertex from the stack. It will pop up all the vertices from the stack which do not have adjacent vertices. Rule 3. Repeat Rule 1 and Rule 2 until the stack is empty. Thank you.